Okay. Now instability in diffusion flames. Okay. What are the possible instabilities we have in the diffusion flames is only one, that is lift off and subsequent extinction. Okay. So, you can see that again I am given the example of the LPG jet flame. You can see that this LPG jet flame is coming out from a very small orifice, what we see in a Bunsen burner is about 0.4 mm orifice, and at a flow rate of say flow rate is such that the velocity of the fuel jet is 13.9 meter per second. You see a flame which is intact. The flow rate is very low because the diameter of the orifice is very low, but you see a good flame where there is no soot production etc. here. But when I increase the velocity of the fuel jet to 15.4 meter per second, you see the flame lifts off to a particular height h. Okay. So, I will say HL, that is the lift off height. So, when you increase the flow rate, the same burner, when you increase the flow rate to 13.9 to 15.4, you see the flame lifts off and it goes to a and goes and sustains at a particular height called HL, which is called the lift off height. Okay. At increased fuel momentum, see when you increase the fuel momentum in a cold jet, what you have seen is when you increase the fuel momentum, the air entrainment also increases basically, correct. So, Reynolds number of the jet is increased. So, as a result of it, the air entrainment will be increased. So, jet spreading rate will be higher and so on, correct. So, when I increase the fuel momentum, obviously from 13.9 to 15.4 the velocity is increased, momentum increases, obviously more air should have entrained. Okay. And the rate at which air is entrained also is higher. So, due to the increased rate of fuel momentum as well as the air supply, you will see that the mixing also will be enhanced. So, proper mixing should have taken place, but why the flame has not formed here? That is because the residence time for the mixture to sustain the combustion there is very low. Okay. The reaction time, the flow time has become close to the reaction time or even slightly lesser than that. So, causing insufficient residence time for the reactant which are formed here. So, it is not burning there. So, you know that the jet velocity decays. So, after a particular distance, you can see that velocities have decayed to a lower value, jet has spread, enough mass of air has come in. In that case, you will see that the velocities are low. So, the residence time is higher, so that the flame sustains at a particular height. But if you try to increase it more and more, then what happens? To some extent the HL will increase and after that it just puts off. So, that is the one of the only one instability what we will see is the lift off, which initiates due to the low residence time for the reactants to burn very near to the burner rim, and we subsequently increasing the flow rate beyond this. At one particular point you will see the flame to be blown off, and this lifted flame is not easy to, it is not a diffusion flame, it is a partially premixed flame as indicated by the color. When you premix the fuel jet with a partial amount of primary air, you will see that the bluish regime was seen. Similar bluish regime is seen here in a LPG flame. So, that indicates that there is a partial premixing which has happened. Obviously, there is a mixing due to the air entrainment in this region, and the mixture is partially premixed in this. You can see this reaction zones here, which indicate that the bright blue color indicating the premixed flame at the base. Okay. So, lifted flames cannot be analyzed using the simple chemical reaction systems. We need reaction rates. Kinetics are going to be important in this. In this case, no kinetics is required in the pure diffusion flame. Okay, slightly higher flow rate. So, 14 meter per second to say around 50 meter per second, you get this, where you need kinetics to analyze the flame. Okay. Similar instability which is demonstrated in a cross flow flame. Okay. So, as I told you, in this stable cross flow flame here, you can see a boundary layer formed. This is the fluid injector, leading edge of the fuel injector. A flame is formed very close to the leading edge of the fluid injector, and it goes like this. And phenomenally, you can see this 2D flame anchoring that is appearing over the entire width of the burner injector, the fuel injector. but when you increase the airflow rate, you can see that from the initial point the flame has moved. So, this is the initial point of the injector, flame has moved away and it is not anchoring properly, you can see this. So, it is no more two dimensional, okay, no more two dimensional, it is called separated flame. Separated flame, it is not two dimensional in nature and you can see it has moved away. So, if you increase the air velocity still the flame will blow off. Okay. So, before coming to that, like a lifted premix flame, we have seen that lifted diffusion flame or oscillatory, it will oscillate, the base will oscillate, tip will oscillate and so on, and it will also be noisy. Okay. And the flame length decreases as a result of positive premixing, that is what is illustrated here, flame length decreases. Okay. Combustion efficiency may decrease, as I told you, more CO, unburned hydrocarbons may result from a lifted flame, because there is no control. When the flame is very close to the rim, then the control will be there, as we saw in the premix flame. When the lifted flame occurs, control is lost. Okay. At a higher fuel velocity, the flame will blow off. Okay. Now, in the cross flow flames, when the air velocity is increased, the flame separates from the anchoring points. This is the anchoring point, separates, moves away, and it is not attached to the width also properly, and it is a separated flame which is not anchored properly anywhere, again like a lifted flame, and again you see that incomplete combustion may occur and other whatever be the disorders what we see in the lifted flames, same will be applicable here also. At a higher air velocity, the flame will blow off. Okay. Now, coming to the opposed flow flames, okay, opposed flow flames basically when I increase the momentum of the fuel and air jets, you can see that the strain rate of the flame will increase, strain rate. Okay. At a particular strain rate, the flame will put off or extinguish, that is called extinction strain rate. Okay. This is the only stability, there is no lift off possible there, but the flame becomes stretched and stretched, and strain rate is increased, so that at a particular point the central the flame will tear up and it will extinguish. Okay. So, this is about the instability of the diffusion flames. So, let us see a couple of work examples. The first one is using non-reacting jet theory. We have already seen the non-reacting jet theory. Let us estimate the length of ethane air diffusion flame, initial velocity of 5 centimeter per second. Please understand that I do not need reactions at all for a diffusion flame, pure diffusion flame I do not need. Just by analyzing the non-reacting jet theory, I can find the flame length. Okay. Initial jet velocity is given as 5 centimeter per second, and the velocity profile issuing from 10 mm pore diameter is uniform. So, 10 mm is the diameter here. So, 2R equal to 10 mm, and uniform velocity is coming out, that is given in the problem, and velocity, the average velocity is 5 centimeter per second. Okay. So, now both the air and the ethane are at 300 Kelvin and 1 atmospheric pressure. So, reactants are the same temperature, and viscosity of ethane is given as 9.5 into 10 power minus 6 Newton second per meter square. So, dynamic viscosity. Then you calculate the flame length with this data, plus you compare the result. Okay, anyway, you have to calculate the flame length basically by using a mixture viscosity like this. So, viscosity of the ethane is given. Try to take viscosity of the air at from a table at the same temperature 300 Kelvin. Then you get the average viscosity calculated as mu air plus mu ethane by 2. Then you have to compare the result what we get from this theory, non-reactive theory, with the Roper's experimental correlation. Okay. The main problem with this, no, you will get an estimate, same order of flame length can be got, but accurate value cannot be got from the theory. That is what we are trying to illustrate here. So, the reaction mixture is stoichiometric, because wherever the flame zone is formed, we can say that stoichiometric mixture is prevailing there. So, C2H6 ethane plus 3.5 is the A value for that, X plus Y by 4, O2 plus 3.76 N2. So, the airflow fuel ratio is calculated 15.98. So, YF stoichiometric, okay, that is calculated, that is the value which will bound the flame, that is the bound the flame area, correct, that is phi equal to 1 contour. So, that will be 0.059, 1 by 1 plus nu, because that is this. Okay. So, this is nothing but 1 by 1 plus nu. Okay. Now, from non-reacting jet theory, the flame length is got by setting r equal to 0, that is psi equal to 0 in the y profile. So, this is the y profile what we have got. Now, try to put psi equal to 0, I get the flame length. Not only psi equal to 0, please understand, I have to also set y equal to y stoichiometric. So, x you take this side, in this side, and yf you bring it here. So, then put this as 0, then you get this relationship. So, yf is taken here and substitute as yf stoichiometric, x is taken to the left hand side and that is put as x is equal to Lf, where the flame length is. So, this is the equation we need to solve, correct. So, from the theory we got this. Now, I put r equal to 0, x I am taking to the left hand side, yf I am bringing to the right hand side to the denominator and substituting yf stoichiometric for the yf to get the flame length. Okay. So, now r is known, ve is known, yfs is known, d is not known. How will you calculate d? Okay. Now, again go for the assumption which we already made in the theory. So, nu equal to d. So, d equal to nu here. So, rho mu by rho is nu. So, that we will do. So, mu is nothing but the average which is given here. So, for air, first density will calculate by P by RT. P is atmospheric pressure, 1 atmosphere is given, divided by molecular weight of the air is 28.84. So, the specific gas constant is 8314 by molecular weight into temperature. So, that is 1.17 kilogram per meter cube. Mu of ethane is given, but mu of air is taken from tables. You can see the Stephen Terns table itself, it gives air properties. We can take it from that, 18.46 into 10 power minus 6 Newton second per meter square. So, now the average viscosity got by taking average of these two, and now d equal to nu, that is nothing but mu by rho. This is mu average by rho. Okay. So, now this is the value. So, now we substitute and get the flame length as 0.66 meter. That is all we can get from the theory. However, when you do the robust correlation, I do not need mu everything, I need only S value. Okay, S value is calculated as x plus y by 4, okay, divided by xO2, or we can also calculate by 4.76 into 3.5 by 1. So, 16.66 is the x value, kilomole, molar basis, kilomole per kilomole fuel. Tf, T infinity or 300, that is given. Everything is known. Qf you have to calculate, pi r square Ve, calculate that. So, substituting you get Lf as 0.09. So, maybe take it as 0.1 meter. From the theory, it is 0.7 meter, 0.66. So, you are getting 7 times lesser from the correlation. So, what is the possible reason? So, this is correct. The robust correlation should be correct because this is the experimental data. Several correlations are visible flame. Several correlations are several experiments have been done and data is got here. However, if you take so what is the discrepancy? This discrepancy is due to what? The reasons are this may not be always correct. The Schmidt number equal to 1. Okay, or main culprit should be the variable density may be required, because when you do a non-reacting jet, the density is taken as a constant. But with temperature, if you try to calculate, so go back and try to calculate here, instead of taking density at say 300 Kelvin and getting the density as 1.17, if you try to take an average temperature and calculate density, maybe that will give a closer this value. So, these are the possible reasons. The theory has several assumptions. So, that is, but one thing what you should understand is the same order of magnitude we are getting, same order. So, this is not this is not 0.1 and that is not say 1 or maybe 2 or something like that. Okay, so the same order of magnitude you are getting. So that is the advantage in the theoretical calculations. Next, the final example. Here we need to design a methane or natural gas fueled burner cooking stove that has number of circular ports arranged in a circle. So, for example, you have a circular burner like this, and there are a lot of circular ports through which methane comes out. Okay, methane comes out and burns. So, this is the top view what I am showing, some holes through which the methane is coming out. Some restrictions are given here. So, what is the condition, design condition? The burner must deliver 2.2 kilowatts. The power of the burner is given. Then on a full load, so there is when I say full load, there is a turn down ratio, full load to lower load or a middle like a lowest load, that ratio is fixed basically. So, let us first calculate for the full load. Okay, now I want 40% primary aeration, because this 40% primary aeration will not allow the mixture to be flammable, and in a domestic cook stove we do not need any flashback. So, now first condition is this, we have to satisfy these two. Second is, for stable operation the loading of an individual port should not exceed 10 watt per meter square, millimeter square. So, the total power is 2.2 kilowatts. When you take all the holes into consideration, the total power generated is 2.2 kilowatts. So, now divided by the total area of cross section, that will be the power per area. So, you take one particular port, the maximum power flux watt per mm square, power flux will be 10 watt per mm square. So, this is the constraint what we have. Okay. Second constraint, the first constraint is given. Second constraint, also at the full load the height of the flame should not be 20 mm from height of flame means from individual port, height of the flame should not exceed 20 mm. So, these are two constraints. So, how will you go designing this? Let us see. Let us take, if n is the number of holes and d is the diameter of the each hole here, then total area of feed of fuel and primary air will be number of holes times the area of each hole, that is the total area which is available. So, okay. So, this is mm square. So, power per mm square is now restricted to 10 watts per mm square. Okay, that means 10 should be equal to 2200, which is total power in watts, not kilowatts, divided by area in mm square. Okay. So, from this we can calculate Nd square will be equal to 280 mm square, or now there are two unknowns here, n and d. So, we have to guess one and fix another and see whether the constraints are met. That is the procedure of designing. So, let us fix one of this. It is normally easy to fix a number of holes. So, 36 holes I am keeping, some PCD, pitch circle diameter, and keeping 36 holes. So, that some minimum spacing will be there between these two holes, any two holes. So, n is chosen as 36 as a first trial. Let us see whether this is last trial or not, because if I choose n and decide on d like 2.79 mm, and if these two constraints 10 watt per mm square, which has already been met, and another constraint is the flame length should not be 20 mm. If this constraint is met, one constraint is already met, if the second constraint is also met, then that is done, that is it. So, now let us calculate the mass flow rate of the fuel. So, that is done by the total mass flow rate of the fuel m dot f into delta Hc, which is the heat of combustion or the calorific value of the fuel, should be equal to 2200 watts. Okay. So, that means m dot f should be equal to, this is the power divided by the calorific value of the methane, 50 megawatts. When substitute it, you get 4.4 into 10 power minus 5 kg per second mass flow rate of the fuel. Then mass flow rate of oxidizer, I want 40% primary air. So, I know the 17.1 is the stoichiometric air flow rate. Okay. See, for 1 kg of methane, I need 17.1 kg of air. So, for 4.4 into 10 power minus 5 kg per second of methane, correct, air will be, and the primary air is only 40%. So, 0.4 into 17.1 into, so this is not 0.4, this should be 4.4 into 10 power minus 5. So, that will be equal to 3.01 into 10 power minus 4, and that is the volume, the mass flow rate of the air. So, what will be the total mass flow rate? Mass flow rate of fuel plus mass flow rate of air, and volumetric flow rate is what we want, that will be divided by the density of the mixture, which is calculated again using the reactant mixture which is shown here. So, you know the mass flow rate of this methane plus 0.4 times 2, this is the mixture what we have. So, mole fraction of air is calculated as 0.4 into 2 into 4.76 divided by 0.4 into 2 into 4.76 plus 1, that is the mole number of kilomoles of the methane also is added. So, mole fraction of air is 0.792 and that of the fuel is 0.208. Now, calculate the molecular weight of the mixture as sigma xi mi. So, that will be the case, then it will get the 26.17 kilogram per kilomole. Now, density is P by RT 101325 divided by R is 8314 by 26.17 into 300. So, this will be the density. Now, once know the density of the mixture, volumetric flow rate of the reactant will be 3.45 into 10 power minus 4, that is this plus this. Okay, 3.45 into 10 power minus 4 is 3.01 into 10 power minus 4 plus 4.4 into 10 power minus 5 divided by 1.063, which is 3.24 into 10 power minus 4 meter cube per second. So, now volumetric flow rate per port. So, there are 36 ports and the total volumetric flow rate is this. What is volumetric flow rate? If you divide it equally among the 36 ports, you get 9 into 10 power minus 6 meter cube per second per port. Now, go for the correlation, empirical correlation by row by. As I told you, these empirical correlations are very useful for designing. So, let us take this. Primary aeration is there. So, S value has to be calculated by using the formula what we have already projected, 1 minus the fraction of primary air, this is 0.4 divided by Xp plus 1 by S fuel. S fuel is nothing but 9.52. When you have no primary air, the methane plus 2 times oxygen plus 3.76 nitrogen. So, in this case you will get S as 2 into 4.76 divided by 1, that will be 9.52 and Xp is 0.4, then you substitute, get the value of S as 1.19. Okay. So, now substitute this in the correlation, Roper correlation, you know the QF for individual port, that is 9 into 10 power minus 6 meter cube per second, TF, T infinity TF are 300, then 1 ln of 1 plus 1 by S, okay, it's 1 by, okay, 1 by S fuel. So, 19.6 mm, this is, you get the flame length as 19.6 mm, which is less than the constraint given 20 mm, that is fine. So, that means the gas what we have done N as 36 is fine enough and we meet both constraints. One is the power loading flux is 10 watts per millimeter square, that is met because D is calculated with that equation, and by calculating the volumetric flow rate and the flame length, we find the flame length to be less than 20 mm. Okay. So, this finishes the topic.